For this video, we're going to look at a power series example, and the question we're going to try to answer is, what is the interval of convergence? So this up here is the form of our power series, and so we're going to define a bit more complicated C sub n and a values than we did in the previous example with the geometric series. So our C sub n is going to equal n over 3 to the n plus 1 quantity, and our a is going to equal -2, which will be our center. And our x, of course, is still our variable. So plugging our C sub n in up here and our a in up here, our power series becomes this. Now our question is, what is the interval of convergence here? So we need to apply a convergence test to it. None of our typical convergence tests really apply here. They don't really help us out. So we're going to just jump straight to the ratio test, which is actually going to help us out. However, just a warning, the ratio test isn't going to be enough. We're going to have to add in a couple extra tests on the end as well. Overall, we're going to have to do 3 tests on this to clearly identify the interval of convergence. So there's going to be a bit of algebra involved in it. But if you recall, our ratio test says that we first find this limit. So it's a limit as n approaches infinity of the absolute value of our a sub n plus 1 term over our a sub n term. And according to the ratio test, if this limit is less than 1, then the series will converge. So we want to figure out for what x values is this limit going to be less than 1, and that's going to help us find our interval of convergence. But first thing we need to do is find a sub n and find a sub n plus 1. So our a sub n is just simply here. So this up here is our a sub n term. Our a sub n plus 1 term, we're just going to add plus 1 to all these n's. So notice when I took this n here, I made it to n plus 1. I make sure and put parentheses around that just to make sure I'm not confusing anything. It's really easy to make that mistake. So I put n plus 1 up here in the exponent, n plus 2 here in the exponent, because I'm just adding a plus 1 to this, for example. Plus 1 to this, and I'm adding a plus 1 to that n as well. So taking these, plugging them into this limit, I plug my a sub n plus 1 in here, my a sub n in here, and I get this limit, which is already starting to get a little ugly, and it's going to get a little uglier too because we're going to have to do a couple algebraic tricks to simplify this. So this is our limit we're looking for. Let's just go ahead and get rid of some of this stuff up here so we can free up some space to work on this. So first thing we're going to do is we're going to take this limit here, and we're going to multiply the top and bottom by the reciprocal of our denominator here. So we take the same thing, this whole thing just goes up here, and we're multiplying it by the reciprocal of our denominator on the top and multiplying it by the reciprocal of our denominator on the bottom. So there's a lot of terms up here, but the point we're doing this is this denominator will just cancel out, and then we just have to multiply this term times the top up here and multiply this bottom term times the bottom down here. So this limit is going to equal this limit up here where I just multiplied those terms through. And what I'd like to do is start canceling some of these things out. However, I can't quite cancel these out because I've got this n plus 1 here over n, and I can't cancel those out straight. N plus 1 over n plus 2, I can't really cancel those out straight. So I've got to do a little bit of algebraic manipulation to do that. But first, let's get rid of this here on the bottom. And what I'm going to do here is I'm going to change this term up top, this x minus 2 n plus 1 term. I'm going to say x minus 2 to the n plus 1 is equal to x minus 2 times x minus 2 to the n. So I just kind of separated out one term in this from this exponent. So now if I do that, it could cancel out with this x minus 2 to the n term down here. And I'm going to do the same thing with this 3 to the n plus 2 term. I'm going to say 3 to the n plus 2 is equal to 3 to the n plus 1 times 3. So I just sort of split this up so that these 3 to the n plus 1 terms will cancel out. So making those algebraic changes, I end up with this down here, where I broke up my x minus 2 term and I broke up my 3 to the n plus 2 term down here. And now I can start canceling things out. So this is where it gets fun. Cancel that out. Cancel these out. And now things simplified a little bit from doing that, which means we're making some progress here. So canceling those out, we end up with this, which is getting simpler. However, I'm still got infinity over infinity form here because I got n in the numerator and in the denominator. So I'm going to go ahead and multiply both sides by 1 over n. And that's going to change this term into a 1 and this term into a 3 when I do that. And now we can finally go ahead and apply this limit as n approaches infinity. So this 1 to the n term is just going to go to 0, and that's really the only thing I needed to apply there. So that we end up here with x minus 2 over 3 are the absolute value of the quantity thereof. And now that we've finally found this limit, recall that the whole point of this was we're applying the ratio test, and we want to make sure that this limit is less than 1. If it's less than 1, we know it converges. So this has to be less than 1, and this is what we're trying to find. So we're making some progress now, but we still got a bit of work to do to find out what our x value is to make sure this is less than 1. So let's go ahead and get rid of this stuff. And first thing we want to do here is we can just multiply both sides by 3. Pretty easy step. And doing that, we get the absolute value of x minus 2 is less than 3. Now here is a bit of a tricky step, but basically, you just have to understand what that absolute value sign actually does. So imagine this quantity x minus 2 in the middle here. Imagine that's positive. That absolute value sign isn't going to do anything at all. So let's take a look at that first case. So this is assuming, just say quantity is positive. In this case, we just end up with x minus 2 is less than 3. And we can just add 2 to both sides. And we get x is less than 5. Which I'm showing in blue here now because it's finally, we're making some progress, and this x is less than 5 is sort of an important conclusion that we've reached. Now we can take the other side of this, and that's where this quantity in the middle is negative. And if the quantity in the middle here is negative, then this absolute value sign flips the sign. So in that case, we flip the sign of our x minus 2, and it becomes negative x plus 2 is less than 3. So from here, we can just subtract 2 from both sides. We end up with negative x is less than 1, and from here we can multiply both sides by negative 1. But recall that when we multiply both sides by negative 1, this is going to flip our inequality here. So doing that, we get x is greater than negative 1. So we're looking for our radius of convergence. Typically, we'll look for our center, and we'll look for our interval of convergence. Now at this point, it might be helpful just to actually plot out this series just to see if we're on the right track with our x is less than 5 and x is greater than negative 1 values. So let's go ahead and do that. So in Desmos, we can just type in our f of x is equal to our sum, and let's just go from 1 to 50. Don't want to give it too many terms. It might take too long to process. Of this particular series was n over 3 to the n plus 1 times x minus 2 to the n. So if we zoom out here a little bit, we can see that it looks like this is going to converge between x equals negative 1, and up here at x equals 5 it looks like it's diverging again. So it looks like we're on the right track with our x is less than 5, x is greater than negative 1. And you can see that our center here is going to be x equals 2, because you can see that's kind of the middle of our interval of convergence. Plus, we already defined a was 2, and that's going to be our center. So having sort of confirmed this on the plot, let's move this to the side. And we can say our radius convergence is 3, because that's the distance from our center, which was x equals 2, to the edge of 5, or the other edge of x is greater than negative 1. So now we can almost find our interval of convergence. We know it's between negative 1 and 5. However, we don't know what happens exactly at x equals negative 1 or x equals 5. We do know that when x is greater than 5, it's going to diverge, and x is less than negative 1, it will diverge, because the ratio test tells us that when this value is greater than 1, it will diverge. But we don't know what happens exactly at negative 1 or at 5. So let's go ahead and test those endpoints. First, let's test the left endpoint at x equals negative 1. So how we're going to do that is we're going to pull back our series up here, and we just take this negative 1 value, and we just plug that up in here for x. So we just get this quantity of negative 1 minus 2, and this just becomes negative 3 here. So we end up with this series. And you notice that negative 3 looks like it could cancel out this 3 on the bottom. However, they're not quite in that exact format. So we can just say that this 3 to the n plus 1 on the bottom is equal to 3 times 3 to the n. We can sort of pull a 3 out of that, and then we can cancel these out. So doing that, we end up with this series where we pulled this 1/3 out front, and now this negative 3 and that 3 to the n will sort of cancel out, or they'll just become negative 1 to the n. As shown here, negative 1 to the n. And at this point, looks like we can apply our test for divergence here. So we're just going to take the limit of our a sub n value here. So taking the limit of this, we find that as n gets really big, this is going to go to plus or minus infinity, which is not equal to 0. Therefore, we can say that this series diverges by the test for divergence when we plug in this x equals negative 1 value up here. So now we can fill in this left part of our interval convergence here. We know this x has to be greater than negative 1, and there's no equal to sign here because that negative 1 is not included in our interval convergence. Having found that left endpoint, we can move on to the right endpoint where x equals 5. And we can just go ahead, as we did earlier, plug that 5 up into here and follow basically the same process. And that 5 minus 2 here just becomes this 3. And now this 3 to the n can sort of cancel out with a 3 to the n plus 1. We're just going to change 3 to the n plus 1 and say that equals 3 times 3 to the n. And doing that, we end up with a series down here, and you can see at this point these terms will just straight cancel out. So we end up with this series here, and we can go ahead and take the limit of our sequence here. And taking that limit, we see that when n approaches infinity, this whole thing is going to approach infinity, which is not equal to 0. Therefore, we can conclude that this series diverges, again, by the test for divergence. So earlier we had that x has to be greater than negative 1, and now we've just determined the left part, which is that x is less than 5. We're not including 5, so we just have the less than here, and we could also show this as our interval with the parentheses here of negative 1 to 5. So this was a lot of steps. You can tell we ended up applying the ratio test, and then we applied our test for divergence twice. So there's a lot of work that went into this. There's a lot of algebra that went into that ratio test to finally come up with this solution here. But that is a little bit higher difficulty example of a power series problem in trying to find the interval convergence, and hopefully this sort of builds the base for Taylor series, which we'll approach next.